Okay then, 2D3. A frictionless horizontal surface. So the plane of paper is my horizontal surface. I have here a spring with constant K1. Here is a mass M. And here I have a spring with spring constant K2. This object is in equilibrium, lying still on the table. I call this x equals 0. And I'm going to place this in the minus x direction over a distance a. A in the minus x direction, I call this the plus x direction. Let us first make the assumption that in this particular configuration, the way I have drawn it, both springs are relaxed. That means they are not pushed in and they are not stretched. Therefore, they do not exert any force on the object M. They are totally relaxed. Now I'm going to put the object here. That means this spring is pushed in, and so if it's pushed in, it will push outwards to the right. It will push this back to equilibrium, and the force will be K1A in positive direction. But of course this spring is longer than it wants to be, so it will pull inwards, so there will also be a force on M in the positive x direction, which is K2 times A. And so the restoring force F, which I write down as a vector equation, equals K1 plus K2 times x. And to remind you that it is in the positive x direction, I will introduce this x roof, and x roof simply represents the unit vector in the plus x direction. I do not like this equation. I hate equations like this because I'm used to seeing here a minus sign. And the only reason why you don't see this minus sign here is that I have moved this object to the minus direction. And so I'm going to change it. I'm going to change it in a more general equation. That doesn't mean this one is wrong, but I'm going to change it in a more general vector equation, minus K1 plus K2 times x. It's a one-dimensional vector equation. If x is positive, the force is driving back to equilibrium, is in the negative direction. If x is negative, as is the case here, the force will be positive. As you see here, it's driving it back to equilibrium in the positive x direction. This represents the equation of a simple harmonic oscillator. And the period of the simple harmonic oscillator, T, this is the period. This has nothing to do with tension, equals 2 pi times the square root of the mass of the object divided by K1 plus K2. The springs act together. That's why you see here K1 and K2. The net force on M is larger due to both springs than it would be if there were only one spring, and therefore on a given mass having a larger force, it's obvious that everything will go faster, and so the period will be shorter. And that's exactly what you see. The larger this value is, the smaller will be the period. And this is very intuitive. Now, it is not so intuitive that this period t is independent of the displacement a. A we call the amplitude. I take the object and I displace it to one side, and then I release it and it's starting to oscillate. And the period of oscillation, which you have here, I'll get back to that, this period is independent of the amplitude, and the amplitude is the maximum displacement from equilibrium. In this particular case, we had A. That is not so intuitive that this period is independent, but I will return to this. Let's first address the issue, what would be the case if the two springs were not relaxed when I start? So suppose I have here again this frictionless table, that's the plane of my paper, and I stretch this one, it's now much longer than in the relaxed position, and I also stretch this one, it's also much longer. This is spring with spring constant K2. And here is the mass m. It would mean then that in this position, in this equilibrium position x equals 0, because it's not being accelerated, it's sitting still, this is equilibrium. It means then that in this situation, which is now my initial condition, there is a force to the right, because this spring is longer than it wants to be, so it wants to contract, so it will pull to the right. This string is also longer than it wants to be, so it also wants to contract, so there will also be a force to the left. I will call that F1. But the two forces obviously must be the same in magnitude, otherwise this object could never be in equilibrium. So this is now my starting condition. And if now I move this object to the side, for instance to the negative x direction, A, then I want you to convince yourself that everything we've done before remains the same. In other words, that the restoring force to equilibrium will be exactly as it was before. Makes no difference that now these springs are stretched. Makes no difference. And therefore that also the object will again be starting oscillating, simple harmonic oscillation, and that the period is precisely as we just stated. Now I will derive this period for you, and I do that through a differential equation. So I write down a one-dimensional differential equation. F equals ma, Newton's first law. This is a vector, this is a vector. Now, A is the second derivative of x, so I can write down for A mx double dot, whereby x double dot equals d2x dt squared. And that now equals minus capital K, which is the equivalent spring constant, in this case K1 plus K2 times x. Why don't I put arrows over here? Well, because this is a one-dimensional vector equation. If x is positive, this minus sign will tell you that the force is in the minus direction. If x is negative, the minus sign will tell you that the force is in the positive direction. So I really don't have to put the arrows over here. Now I'm going to combine these two, and I get the famous equation that you will see a zillion times before this course is over. Mx double dot plus Kx equals 0. This is the famous equation of a simple harmonic oscillator. The solution to this equation I will give you for now, that x as a function of any moment in time, x is the position of this object m, equals some amplitude x0, which is the maximum displacement from equilibrium, times the cosine of omega t plus alpha, or it could be the sine of omega t plus alpha. Omega we call the angular frequency, which is 2 pi divided period t. This has nothing to do with tension. This is the number of seconds for one complete oscillation, and that is the square root of k over m. The frequency in terms of how many oscillations per second equals 1 divided by t. So that is the number of oscillations per second, which we sometimes often call hertz. And omega is often expressed in radians per second. x0 is the amplitude, the maximum displacement from 0. And alpha is a phase angle which is entirely dictated by the initial conditions. There is really not that much physics in alpha. I can make alpha 0 if I want that. I can release the mass m at t equals 0, and I can do that with 0 speed. And if I do that from a location x equals plus a, x equals a, then x as a function of t would be x0 times the cosine of omega t. You can check for yourself that by stating the initial conditions the way I did, I have made alpha 0. The velocity as a function of time is the derivative of this, so that gives me a minus omega. Oh, I was going to make this an a. Omega times a times the sine of omega t. Notice that at t equals 0, the velocity is indeed 0. That was my initial condition. At t equals 0 is 0 speed. And also notice that when t is just a hair larger than 0, the velocity is negative. That's clear because when I release the object from plus a in positive x direction, it wants to go back to equilibrium, and so the velocity is in this direction, and therefore the velocity is negative. If the velocity were in this direction, the velocity were positive. So that's all beautifully taken care of by algebra, and now we get x double dot t, which is a as a function of t, that equals minus omega squared times a times cosine omega t, which is also minus omega squared times x of t. So now what you can do, you can substitute this x in here. Oh, where is my differential equation? No, I have to substitute it in the differential equation. I'm sorry. I have to substitute this x in here, and I have to substitute this x double dot in here. And what do I find then? That this equation, this differential equation, is only and only satisfied if omega equals the square root of k over m, which is what I stated earlier verbatim without proof. Here you have it, square root of k over m, and therefore that the period of one oscillation equals 2 pi times the square root of m over k. And I repeat myself, the frequency, how many oscillations per second, is 1 divided by the period. And you notice, which I stated earlier, that this period is indeed independent of a, which now I proved. And that is by no means so intuitive. I find it always amazing, but it is very characteristic for a simple harmonic oscillation that the period of oscillation is independent of how far you displace it from its equilibrium point. If you look at this equation in more detail, you see that the larger k is, the smaller the period. I discussed that earlier. That is rather intuitive. The larger the mass m is, the lower the acceleration will be for a given force on the mass. If I make m larger, the acceleration will be slower. Therefore, the whole motion will be slower. And if the motion will be slower, obviously, it will take longer to complete one oscillation, so t will be higher. So you see, indeed, if m is higher, then also t is higher, and that, of course, is intuitively very pleasing. In general, the phase angle alpha will not be 0, but I have made it 0 by choosing my initial conditions very appropriately. And you can very often do that. So now we get to the last part of this problem set. Let me do a time check. Boy, I'm 15 seconds ahead of time. That's a real treat. The last part is asking you the following. I now take this same system, K1, with mass m, K2, and it's now vertical. And there is gravity. Let's first take the situation that there is no gravity. That's the situation here, and here I have equilibrium. Now all of a sudden I turn gravity on. Let this be the floor, and this object will sag because of gravity. It will sag over a distance s. S stands for it will sag. And so the new equilibrium position will now be here. This spring will be longer than it would prefer to be, and this spring is shorter than it prefers to be. So if I take this object M and I look at the forces now in its new equilibrium, then there is of course mg. That's clear. But now this spring is shorter than it wants to be, so it's going to push up. So it will push up with a force F K1, which equals K1 times S. That's the magnitude. This one is longer than it wants to be, so it wants to contract. So it will also push up with a force F K2, and the magnitude of that force in upwards direction equals K2 times S. There has to be equilibrium. The sum of all forces in this direction will have to be 0. In other words, mg must be equal to K1 plus K2 times S. And this, if you want to, allows you to calculate what S is, how far this object is sagging. Now comes an interesting portion, an interesting part of this problem. Suppose now from this new equilibrium position, I move the object either down over a certain distance, or I move it up over a certain distance, and I let it do its thing. And the displacement from this new equilibrium position, I call this now y, so that we don't have any confusion with my x before. I want you to demonstrate now that you will get now F equals ma equals m y double dot equals minus capital K times y, where capital K equals K1 plus K2. And this again is the same simple harmonic oscillation that we had before. Again, we find that omega equals the square root of capital K over m. The period is unchanged and the frequency is unchanged, and both are independent of the amplitude by which I displace it from 0. And so, even though I've left you with this a little bit, the bottom line is that even when I put this whole system in gravity, and so when there is the sag, given the new equilibrium, when I displace it away from the new equilibrium, the object will oscillate with exactly the same period, exactly the same frequency as it did before when we had the system on a horizontal frictionless plane. You may think that's so obvious. I find it always a little bit surprising. But yes, when you come to think about it, maybe it is obvious.